In topic 6, convergence of the finite element approximation to the Helmholtz problem. Now that we have the required interpolation operator results stated in the previous topic in Theorem 26, we can return to applying CS lemma to the convergence of the finite element approximations to the Helmholtz problem. Corollary 27, the degree K Lagrange finite element approximation UH to the solution U of the variational Helmholtz problem satisfied. The error UH minus U in H1 norm is finite, is bounded by CHK UHK plus 1 norm. CS lemma gives us error estimates in the norm of the space where the variational problem is defined, where the continuity and causivity results hold. In the case of the Helmholtz problem, this is H1. We would also like to estimate of the error in the L2 norm, and it will turn out that this will have a more rapid convergence rate as H converge to 0, means that the mesh become getting smaller. Theorem 28, elliptic regularity. Now let's W solve the equations. This is Helmholtz equation. W minus del gradient square W equal to F, where del W del N equal to 0 on the boundary. On a convex domain omega with F in L2, then there exists constant C greater than 0 such that the semi H2 norm is bounded by C, F in L2 norm. Similar results hold for general elliptic operators such as Poisson's equations with the types of boundary conditions discussed above. Elliptic regularity is great to have because it says that the solution of the H1 variational problem is actually in H2, provided that F in L2. And now use this to obtain the following result using the Aubin-Nitsche trick stated in Theorem 29. The degree K Lagrange finite element approximation UH to the solution U of the variational Helmholtz problem satisfied. So the error in L2 norm UH minus U is bounded by CHK plus 1 U in HK plus 1 norm. Thus, we gain one order of convergence rate with H by using the L2 norm instead of the H1 norm. So you can find the details in the reference stated here. So in conclusion, we complete our analysis of the convergence of the Galerkin finite element approximation to the Helmholtz problem. Similar approaches can be applied to analyze other elliptic PDE by using the similar steps. First, you need to find a variational formulation of the PDE with a bilinear form that is continuous and coercive and hence well posed by Lex Milgram on HK for some K. Then find a finite element space VH, a subset of HK. For H1, this requires a C0 finite element space, and for H2, a C1 finite element space is required. In the next step, the Galerkin approximation to the variational formulation is obtained by restricting the solution and test function to VH. Next, continuity and coercivity and hence well-posedness for the Galerkin approximation is assured since VH is contained in HK. This means that the Galerkin approximation is solvable and stable. Lastly, the estimate of the error estimate in terms of H comes from CS lemma plus the error estimates for the nodal interpolation operator. That's all for topic 6.4, basic convergence for finite element. Thank you.